through the delicate glazes of the Venetian masters, the sharp chiaroscuros of the Caravaggists, or the vibrant impastos of the Impressionists, color never ceases to fascinate. It is, and has always been, the main attribute of the painter. The enigma of color is a paradox. Each artist contributes to unravel its secrets through his or her work, but the mystery seems to become stronger with each new attempt. Color is such a profound mystery that each discovery or innovation opens new paths to unexplored, ever larger, ever more unknown territories. Thus, a question arises: how to understand color? What place should be given to theory? The most important thing is that color theory should not be an obstacle to spontaneity. It shouldn't be something you have to check in the middle of a painting. Theory must be developed before the painting begins. There is no point in using dozens of small colored cards, diagrams, or color wheels if it doesn't bring an artistic benefit. If used incorrectly, this type of tool can only be an obstacle to creativity. Color theory should only be there to provide relevant knowledge that can later be used without actually thinking about it, like a second language. It's obvious that color theory is sterile if the knowledge cannot be transposed into everyday practice. Would it be said of someone who knows music theory by heart that he's a good musician if he or she has never touched a single instrument? Certainly not. And similarly, color theory, to serve the artist, must not be purely abstract. It must be connected to practice. Thus, it is practice that will serve us as a guide for our color theory. Anything that has no potential for a practical application will be excluded or only briefly mentioned. 3 fundamental questions will guide us through this course. 1. How to find the right color. 2. How to use the colors to represent things. And 3. How to harmonize colors and compose with them. In addition to this program, you will find a summary of all the most important information in the companion document to help you remember the key concepts. This guide also contains all the color wheels, the diagrams, and all the illustrations that will help you take this course. I would like to start with a question that will surely seem strange, but that will give us a good introduction. Does an object have a color when you don't look at it? Let's take this paint as an example. If we follow our first intuition, it's easy to think that if we see red when we have our eyes open, the color remains the same when we close our eyes. But if our mind makes us think that color resides in objects, reality is that we must answer no to this question. Indeed, from a theoretical point of view, color is not a property of objects. At first sight, everything suggests that color is sort of painted on the surface, but it's only an interpretation of our brain. From a physical point of view, color has no substantial existence in objects. This is easy to demonstrate. Cut off the light and no object has any color. Color is therefore the result of an interpretation of our visual system in response to light stimuli. Now, let's find out what makes the color of an object. Everything starts with light. Without light, there is no color. Light has wave properties, like a skipping rope swung in turn by 2 children. The distance between 2 peaks is called the wavelength. It is the wavelength that determines the hue of the light. The longest of the visible spectrum is red, and the shortest is violet. Beyond the limit of the visible spectrum are infrared and ultraviolet that we cannot see. Visible light is an electromagnetic radiation with wavelength ranging from about 400 nanometers to 700 nanometers. From a physical point of view, the visible spectrum is only a tiny part of the electromagnetic radiation field. Now let's look at the object. We said that it has no color as such. The surface of the object operates as a wavelength filter. Some can bounce off its surface, but others can't. Some are therefore absorbed, while others are reflected. An object only has the color of the wavelength it rejects. A red object absorbs the wavelength of all colors except red. A black object absorbs all wavelength, and a white object reflects almost all of them. We're almost there, but all we need for a color to exist is a visual system to see it. The eye is the result of a long evolution among species. Its role is to react to light radiation. The different sensory senses on the retina each have a preference for a certain wavelength. When the red light reflected by the object reaches the retina, all three types of senses are stimulated at the same time with different intensities. The brain then processes all the information and translates it to give the sensation of color. Color is therefore the perception we have of the different wavelengths that make up visible light. We see that, contrary to our first intuition, the color of an object is entirely subjective. Humans don't see the same world as other animals. Many animals do not see as many colors as we do, but some see colors that we cannot even see, like UV, for instance. Moreover, there are differences between people. Color perception can depend on age, environment, individual culture. Have you ever wondered if the red that you see is the same red your friend sees? How can we know that? There is a science of color measurement called colorimetry. It's very useful for accurately measuring and reproducing colors from one object to another. However, it's a science that cannot penetrate the most subjective and intimate aspects of color. What color is to you and what it is to me, it's impossible to measure. Who can deal with this everlasting mystery? There is one answer: the artists. In a way, each artist creates a unique interpretation of color to offer it to the world. The subjectivity of color is not an issue for the artist. The work of art exposes how the artist feels and how he or she breathes color. Therefore, the goal of this course is to give you all the necessary knowledge so that you can really express the right color. That is, the color that's within you. These samples do not all have the same color. But is that all we can say about it? The word color is often used very generically because the needs of our everyday life do not require us to be very precise. Unfortunately, this is not enough for painters. Colors should be broken down into three main components: hue, value or brightness, and chroma or purity of hue or saturation. Each of these, although linked, can be modified separately. For the sample A, only the hue was changed. The value and chroma are identical. On the sample B, only the value was changed. The hue and chroma are identical. And on the sample C, only the chroma was changed and the value and hue are identical. These three concepts are absolutely essential for this whole program. It is crucial to understand them before going any further. Hue is a property that's often confused with color itself in everyday vocabulary, yet it is only one aspect of it. The hue of a color corresponds to the wavelength of light or to the mixtures of wavelengths, as for colors made up of a mixture of violet and red. Like the colors of the rainbow, the hues are distributed from the longest to the shortest wavelength. In the basic vocabulary, we use 11 main words for colors. If we remove white, black, and gray, and brown from the list, which are not strictly speaking hues, we have 7 basic hues: red, orange, yellow, green, blue, violet, and pink. There is no difference in nature to switch from one hue to another, only a difference in degree. There is no limit between red and orange. The wavelengths of the different hues are gradually distributed over the entire visible spectrum. It is impossible to determine a precise number of hues, as the number of gradations and combination is theoretically infinite. Our eye is not able to perceive all the imaginable hues. However, its ability to distinguish hues is quite remarkable. If we count the differences in value in chroma, it's estimated that the human eye can distinguish between 2 and 8 million colors. The value of a color is its perceived brightness. This property, sometimes called luminosity, is what makes us say that a color is light or dark. More precisely, the value of a color is the amount of light reflected per unit area. 3 main factors influence value. The first factor is the amount of light emitted by the light source. If you light a flat object like this card with a very small lamp, its value or its perceived brightness will be low because it will only reflect a very small amount of light. Second factor, the luminous reflection properties of the surface. In the scientific lexicon, the relationship between the amount of incident light and the amount of reflected light is called albedo. A perfectly white surface, like snow, has an albedo close to 1 because it reflects almost all the light it receives, so its value is very high. A neutral gray surface theoretically reflects half of the light and absorbs the other half, so its value is average. Finally, a black surface like coal with an albedo close to 0 absorbs all the light it receives and therefore has a very low value. Last but not least, the value depends on the angle of incidence of the light rays. The illusion of volume comes from this distribution of values on the surface of an object depending on the angle of incidence of the light. With only values, you can represent volumes and shapes and create the impression of shadows and light. Black and white photographs and movies show only values and they are perfectly understandable. Chroma, sometimes called saturation or hue purity, is the degree of purity of a color compared to a neutral gray. This property is what makes us say that a color is more or less intense or more or less vivid. We will use the term more chromatic or less chromatic. If you use a photo editing software, you might be familiar with the notion of saturation, which is almost identical, although a little bit different. Simply put, saturation describes the intensity of the color of an object emitting its own color, such as a computer screen, for instance, while a chroma describes the intensity of the color of a real object compared to a neutral gray placed in the same light. Saturation is measured in an absolute way, while chroma is always a relative value. Chroma is measured in comparison to a neutral gray of the same value. In this illustration, the sphere on the right is said to be more chromatic than the one on the left, which is much closer to gray. The higher the chroma of a color, the more steps separate it from a neutral gray. For the sphere on the right, 4 intermediate gradations can be created before reaching neutral gray, whereas the sphere in the middle is only 1 step away from neutral gray. One could argue that it is possible to have an infinite number of steps, and this is true in theory, but no human eye is able to see so many subtle nuances. For the color system of this course, I have chosen to limit myself to 10 steps, which is more than enough for an artist. However, it should be noted that there is no maximum limit to chroma, nor to the number of steps that can theoretically be counted. The basis of our color systems must be human vision, and the basis of our method must be artistic utility. Thus, it's not necessary to use more than 10 levels of chroma. On the other hand, what's very important is to understand how chroma is affected by the 2 other dimensions of color. Chroma both depends on value and hue. Let's see how it depends on values first. If we start with the color sample C and change its value, we observe that as it becomes darker, it becomes closer to a neutral gray. This means that the darker a color becomes, the less chromatic it becomes. But it doesn't mean that making the color lighter will increase its chroma indefinitely. As we can see here, if we lighten sample C, we see that we reached a peak that allows us to distinguish 10 different chromatic gradations before reaching neutral gray, and then this amplitude decreases as the value approaches white. We will call this peak home value or peak chroma value. It's the highest chromatic potential of a given hue. Now we've seen how chroma is affected by value, but we also see that chroma depends on hue, because each hue has a specific home value. A red tends to be more chromatic for average values, while a yellow will have its peak chroma value among the brightest values. A blue, on the other hand, will reach the maximum chroma for rather dark values. This means that the most chromatic red that can be created will not have the same value as the most chromatic yellow that can be created. Understanding this phenomenon is crucial for an artist. It explains why it is impossible to create a dark yellow as bright as a light yellow, and why a light blue does not have the same intensity as a deep, dark blue. Without going into detail, let's explain how our vision works. A common idea is that we have 3 types of senses: red, blue, and green. It's a simplification. Our eye has 2 types of light-sensitive receptors: rods, which work when there is very little light, and cones, which detect colors. There are 3 types of cones. Each is sensitive to a part of the visible spectrum: short, medium, and long wavelength, S, M, L. These cones cannot be assigned to blue, green, and red respectively because their sensitivity ranges overlap widely. However, we see that the peak of the S cone is in the range of blue, the peak of the M cones is in the range of green, and the peak of the L cone is in the range of red. To simplify, we can admit that there are actually blue, green, and red cones. But we cannot understand trichromacy if we imagine that these cones sort of capture each color separately. If this were the case, how could we see yellow? Indeed, when yellow wavelength reaches the retina, there are no yellow-specific senses to receive it. First of all, it should be noted that a yellow object doesn't emit just one yellow wavelength, but an entire spectrum which covers a whole set of different wavelengths peaking in the yellow area. If we can see yellow, it's because all 3 types of receptors are always stimulated at the same time at different degrees of intensity every time light reaches the retina, regardless of the wavelength. At this point, things get tricky, but I'll try to make it simple. The cones don't just send the information directly to the brain. There is what's called an opponent process that connects the cones in pair of opposite colors, black and white, blue and yellow, and red and green. The combination of trichromacy and opponent process makes all color combinations possible. It also allows us to perceive colors that are not even part of the visible spectrum, such as pink, magenta, and all the nuances between red and violet. They actually do not exist in the form of individual wavelength, but yet we can see them as mixtures of other wavelengths. Metamerism is a phenomenon that explains that the human eye can't distinguish between an orange formed solely by orange wavelength and an orange formed by a mixture of yellow and red wavelength. Two colors are called metameres if they have different physical spectra, but the human eye sees them both as equal. Metamerism is the visual mechanism by which we can mix paint to form new hues. Thus, when a painter mixes yellow and red, he or she obtains a combination of the yellow spectrum and the red spectrum that has exactly the same appearance as the orange spectrum for the human eye. Since the light contributes to the formation of the spectrum that reaches the eye, lighting conditions play an important role in the phenomenon of metamerism. Depending on the temperature of the light source, the color of the object is different. This jar of oil appears yellow if it's illuminated by white light. But if it is lit by cooler or warmer light, the colors needed to paint it will be very different. Your eyes naturally adjust to this, but for a painting, this changes everything. Just like if the light was yellow, green, blue, or red, if light changes, the color of the whole changes. If you paint in a candlelit room, you'll see that the colors that you have painted look very different when you take your painting outside. It's important that the lighting of your canvas is homogeneous and of neutral temperature. The temperature of a light source is measured in Kelvin. The ideal temperature for artificial light source in your studio is around 5,000 kelvins. It's the closest to neutral daylight. You can find LED lamps that let you adjust 5,000 kelvins. As for natural light, a north-facing orientation provides the ideal lighting for a painter. Our vision is particularly adapted to metamerism. Light constantly changes around us, but fortunately, our brains don't let us think that this is the color of the object that constantly changes. It sees light variations in a dynamic and adaptive way to preserve the integrity of the object. This phenomenon is called color constancy. In this famous optical illusion, we see an orange tile and a brown tile. Our brain interprets this tile as being part of the shadows, therefore it sees it as a dark version of what should be a light orange, whereas this tile is seen as being part of the light, so it is seen as a light version of a dark brown. In reality, they both have the same color. This is due to color constancy. Our brain doesn't just pick colors out in the world, it interprets them in their context. We can also take the famous example of the white and gold or black and blue dress that has caused so much debate on social media. Some people see the dress as gold and white, others see it as black and blue. Here again, color constancy is at play. It should first be noted that the photo is of extremely poor quality, with a white balance and an exposure that will make any amateur photographer scream. This poor quality completely blurs the light context of the scene. Thus, it's impossible to know if the dress is lit by a cool blue light or a warm yellow light. And in this absence of context, our brain faces ambiguity. Some people lean towards cool light and see the dress as white and golden. Others lean towards warm light and see the dress as blue and black. I'm going to reveal the secret. In reality, this famous dress is black and blue. If we adjust the exposure level of this picture, we can see it. In short, this picture of horrible quality shows us how much our vision of color depends on context and our subjective interpretation. It's not just about light stimuli, it's also about how our brain sees the context and understands the colors. Let's see how different colors are produced by colored lights or light-emitting objects such as computer screens. This is a process called additive mixing. In the 17th century, Newton discovered that white light can be decomposed into multicolored rays and then recomposed again into white light. From these observations, he came up with the first modern color wheel, in which colors are organized based on their hue. To be more precise, it was the first hue wheel in which black and white were not included, contrary to the previous models. This discovery was so important that today the word color and the word hue are the same for most people, and black and white are often seen as non-colors. For aesthetic and philosophical reasons, Newton chose 7 hues, like the number of notes in the octave in music: red, orange, yellow, green, blue, indigo, and violet. He distributed these hues around the circle according to the proportions of the Dorian musical scale. Note that what Newton called blue would be called cyan today, and indigo would be what we call blue. However, artists realized that it was impossible to use Newton's wheel to paint. So this discovery, although influential, did not upset the routine of most artists, who continued to use the blue, red, and yellow primaries that were known since the Renaissance. Indeed, Newton's color wheel is based on additive mixing, and paint is subtractive. In subtractive mixing, all colors combined make black, whereas in additive mixing, all colored lights make white. Later, at the beginning of the 19th century, Thomas Young discovered that there is no need to combine all the colors of the spectrum to create white light. 3 are enough. Red, green, and blue lights in equal proportions give white. Black is obtained in the absence of light, so the primary colors are red, green, and blue, and they give secondary colors which are yellow, cyan, and magenta. The additive process always gives a mix that's lighter than the 2 original colors. For painters, this representation of color mixing seems very strange. Painters know that it's impossible to get white out of red, blue, and green paints. Indeed, paint mixtures are the result of subtractive mixing and not additive mixing. For objects that absorb light, the mixing process is called subtractive mixing. Everything is inverted compared to the additive model. Subtractive mixing is used by painters and printers. White cannot be obtained by any mixture. White pigments must be used, or the white of the surface must be preserved. Each colored substance placed on the surface will subtract a certain amount of luminosity from the white surface and from the previously painted colors. This is why this model is called subtractive. The discoveries of modern colorimetry have shown that the ideal subtractive primary colors are cyan, magenta, and yellow. We can notice that these are the secondary colors in additive mixing. These pigments are ideally equidistant from red, blue, and green. Therefore, they offer the best balance and the widest possible range from three pigments. These are the primary colors used by most printers. Subtractive mixing always produces darker mixtures than the original colors. In theory, mixing the three primaries gives black, but in practice, adding a black pigment creates better dark colors. This is why most printers add black to the three primaries to give the system CMYK, cyan, magenta, yellow, and the key black. Two sets of primary colors can be distinguished. In additive mixing, the ideal primary colors are red, blue, and green. The secondaries are cyan, magenta, and yellow. In subtractive mixing, the ideal primary colors are cyan, magenta, and yellow. The secondary are red, blue, and green. According to the commonly accepted definition, colors are primary if they cannot be obtained by any mixing and if they allow to mix all the other colors. So far, we have accepted the most common definition, but a closer look will show us that not everything is so simple. For subtractive mixtures in particular, the notion of primary is very misleading as it is. First of all, because there seem to be two functional models at work. On the one hand, the cyan, magenta, and yellow model used by printers, and on the other hand, the more traditional red, yellow, and blue model used by artists and still taught in most art institutions. Then, it is wrong to say that primary colors cannot be obtained by any mixing. For example, by using quinacridone rose and cadmium yellow, we can obtain a red as chromatic as the so-called primary red of the red, yellow, blue model. Or by using a phthalo blue and phthalo green, we can get a color that actually matches the cyan primary of the cyan, magenta, yellow model. Finally, the definition of any individual color itself is ambiguous. Remember what we saw earlier. From a physical point of view, there is no difference in nature from one color to another. So I can call magenta what you would call red, or call blue what you would call cyan. This is a confusion that has occurred in the history of color theory. Before the words cyan and magenta were common knowledge, these colors were often referred to as blue and red, and their exact hue has changed significantly over time. But even today, who can really say what exactly is a magenta or a cyan? Similarly, for primary yellow, which is less debatable, you may find that the yellow I choose as a primary is too orange and prefer a greener yellow. In short, the infinity of shades makes the definition of primary color difficult to grasp. So in the end, what are the real primary colors? Red, yellow, and blue? Or cyan, magenta, and yellow? And which model is right? In reality, both models are correct. In fact, it's mostly the definition of the primary color that is wrong. Here's the definition that we'll use from now on for primary colors. A color is primary if it is part of a set of colors combined to form a range of mixtures called a gamut, and if it is impossible to obtain it by mixing the other colors in the set. This definition changes the usual idea of primary colors. It means that the primary colors can be more than 3. They can be 4, 5, or 6. An artist who has 6 colors on his palette actually has 6 primary colors, as long as none of them can be recreated by mixing the others. However, it should be noted that because of our trichromatic vision, the number 3 makes the most sense. It also means that primary colors are not unique entities that are impossible to recreate, and that they cannot create all the colors that exist, only those that are part of their gamut. Primaries are not universal, they are only unique within their initial set. Finally, it means that any color can play the role of a primary, with more or less success depending on the gamut that is desired. Thus, we can perfectly accept the common definition of a primary, provided we understand that these are only the ideal primary colors we are talking about. That is, the 3 pigments from which the widest gamut can be created. In this regard, red, blue, and yellow do not form a set of ideal primaries, because the gamut of these 3 colors is rather limited. If we look for the pigments that are the closest to the ideal subtractive primaries, then cyan, magenta, and yellow are the best suited for this role. We could call them the true primary colors, but it would suggest that the others are false, and this isn't the case. The notion of primary is imaginary, like the equator line for geographers. It has no real existence, but it can be used as a reference point. By convention, I'll continue to talk about additive primaries for red, blue, and green, and subtractive primaries for cyan, magenta, and yellow. The notion of complementary color is fundamental both in theory and practice. 2 colors are complementary if they are diametrically opposed in the color wheel. But you guessed it, the problem is, what if we don't have the right color wheel? And what exactly is the right color wheel? We need a better definition. Theoretically, complementary colors are antagonistic. This means that one is composed of all the nuances of the spectrum that are missing from the other. Look at this example. Here are 2 complementary colors, cadmium red and cobalt teal blue, with a graph showing their spectral reflectance. As you can see, cadmium red covers most of the wavelength that cobalt teal blue doesn't cover, and inversely. The visual complement of a color can be physiologically determined by the phenomenon of retinal persistence. Here's how it works. I'm going to display a set of squares on a white background and ask you to stare at the dot in the middle for about 20 to 30 seconds. When I remove the squares, I'll ask you to keep your eyes on the dot, and if you want, you can let your eyes blur out. And don't move for another 10 seconds. Now, keep your eyes centered. You should see all the complementary colors appear. Red becomes cyan, magenta becomes green, and blue becomes yellow. This is how we define the visual complementary colors. Let's go even further and experiment with a painting. I'm going to show you a painting whose colors have been inverted. I'll ask you to check that the video is in full screen and to stare exclusively at the center of the cross. Move your head a little bit closer to the screen so that the painting covers most of your field of vision. Now, don't move and keep your eyes on the center of the cross. The picture will soon change, but I ask you to keep your eyes on the cross. Ready? From the corner of your eyes, you should see that the colors are back to normal. The red of the Christ's robe, the green of the forest, and of course the blue of the sky. Now, step back and look at the face of Christ. Yes, that's right, all this time the picture was in black and white. Surprising, isn't it? All this time, you were looking at a black and white image, and the colors were just an effect of retinal persistence. Here are the original colors. In case you were wondering, this is not an effect of screens. You can do the same experiment with paint on a white surface. The phenomenon of visual persistence is an effect of our visual system, how it works. On a screen or with paint, here are the approximate couples that we can get. Red is complementary to cyan, yellow is complementary to blue, and magenta is complementary to green. It should be noted that these pairs do not work in the model where red, blue, and yellow are considered ideal primaries. In this one, the supposedly complementary pairs are red-green, yellow-purple, and orange-blue, and as you can see, they do not match the observations. Theoretically, the mixture of two complementary colors gives a neutral gray. Look at what happens when you add the spectrum of cadmium red and cobalt teal blue. The result is an almost entirely straight line. It means that it is composed of the same proportion of all shades. It's neither red, nor yellow, nor blue, nor green. In short, it's a neutral gray. But this is a rather rare example because in practice, paint mixtures produce very different results depending on the pigments. Visual complements and pigmentary complements are significantly different. The behavior of a pigment is much more unpredictable than what the visual complementary suggests. One pigment can be the complement of several colors on the opposite side of the wheel, and two paints of almost identical colors can have completely different pigmentary complement. For example, cadmium red is complementary to cobalt teal blue, which is almost diametrically opposite in the wheel, but it is also complementary to phthalo green blue shade, also Prussian blue, or phthalo turquoise. At the same time, cobalt teal blue is complementary to Venetian red, which is more orange than cadmium red, but with naphthol red or quinacridone red, it gives a mixture that's clearly purple. Another example, orange-yellow pigments such as yellow ochre are theoretically complementary to ultramarine blue, but in practice it often happens that the mixture of the two draws slightly towards green, and it turns out that the best complementary pigment to yellow ochre is actually ultramarine blue violet hue or ultramarine violet. When two complementary pigments are mixed gradually, the result is not necessarily a straight line passing through the center of the wheel. Quite often, rather than a straight line, the pigments form an arc. Depending on the nature of the two pigments and their tinting strength, the arc can be more or less curved. Everything pigment related is very chaotic. Not only is the color wheel a simplification, but pigments also have behaviors that makes their mixtures very uncertain. We cannot simply start from two visual complements and accurately predict the result of a paint mixture. So what can you do if you want to find which pigments are complementary? The best thing is still to look at the color mixing wheel. I can't give you a complete list because it's too chaotic. Pigments opposed, or at least somewhat opposed, have a good chance of being complementary. Just try and see if it works. But if you want to create a very perfect neutral gray, keep in mind that because two complementary pigments never mix evenly, you will most likely need a third pigment to adjust the hue at some point. If the mix pulls towards green, it must be adjusted with magenta. If it pulls towards red, it must be adjusted with cyan, and so on. Use the complementary pairs. It's a subtle balance to find. That being said, keep in mind that this is not essential to have a perfectly neutral gray. Playing with complementary colors can bring a wide variety of grays. If you want to avoid creating boring grays with white and black, you can practice using complementary colors. They can bring incredible variety to the neutral tones in your paintings. Gamut is an important notion to mix, harmonize, or modify colors. Let's first go over the definition one more time. In painting, the gamut is the set of colors that can be obtained by mixing from a selection of primary colors. For example, a palette composed of cadmium red, cadmium yellow, and ultramarine blue has a gamut formed by this triangle. This means that this color can be obtained by mixing, while this one cannot because it is out of gamut. As we saw earlier, the widest and most varied gamut that can be obtained from 3 primaries is formed by cyan, magenta, and yellow. The more mixing primaries, the wider the gamut. Thus, a palette formed of 12 colors will cover a much larger surface than a palette formed of 3 primaries. But it's not just about number, because a palette of 12 dull colors will also have a very limited gamut. That being said, the goal of a figurative painter is not always to have the widest possible gamut. The gamut only defines a field of possibilities. A very wide gamut gives the possibility to mix vivid purples and bright greens, but these colors might not even be needed all the time. The gamut needed to paint the vast majority of subjects is actually pretty limited. Most of the colors in the world around us are in the shades of gray or brown, which is why limited palettes work in most cases. The gamut can be reduced or changed to get various chromatic moods. Take the gamut formed by blue, red, and yellow, for example. One can decide to use purple instead of blue to obtain a gamut centered around warm colors. Another thing that can be done is to neutralize one of the mixing primaries to shorten the gamut. For example, take ivory black instead of blue. A very restricted gamut can also be obtained by using only 2 pigments, for example ultramarine blue and burnt sienna, with the addition of white. This makes it possible to create paintings in color as if it was monochromatic. It's also possible to imagine a gamut formed by 4, 5, 6, or as many mixing primaries as necessary. There are many ways to sort colors. Color theory is full of systems of all kinds. Some are more useful than others for painters. Before presenting a color system for this course, it's important to remember one thing. Everything related to color classification is subject to debate and interpretation. Colors have no real order in nature. Their wavelengths gradually differ, but there are no boundaries, no differences of nature in physics between a red and a yellow and a green, etc. Any classification system is therefore always arbitrary. How colors are named, how they're organized, how far apart they are, all these points are open to debate. These topics involve science, but also psychology, our social-cultural codes, and our artistic traditions. There is no unified color theory that's accepted by all. The painter with his colors is like a musician who has to invent his notes before playing. The traditional color wheel is articulated around yellow, red, and blue. It's a very widespread model, the most well-known among artists. This model is deductive. It is based on the result of mixing three primaries. This means that the three primary colors are the starting point and that, in theory, all other colors can be mixed without adding new pigments. Since red, yellow, and blue are the three primaries of this model, the shades are distributed on the wheel like in a triangle. As an example, we can take the 12-hue wheel by Johannes Itten. The three primaries mixed together give the three secondaries, purple, orange, and green. And finally, the secondaries mixed with the primaries give the tertiary colors, yellow-orange, red-orange, red-violet, blue-violet, blue-green, and yellow-green. The traditional model has evolved significantly over time. It turns out that many artists use the word red for a pigment that we would call magenta today, just as the word blue was often used for a pigment close to what is now called cyan. So in a way, the red, yellow, blue model is a slightly different version of the cyan, magenta, yellow model. Cyan and magenta are not anchored in our conceptual vocabulary. It is still difficult to agree today on what cyan and magenta really are. In this regard, the best is to rely on industry and printing standards. The use of magenta, cyan, and yellow primaries, to which we add black, is not arbitrary. It's based on research in colorimetry and made possible by the improvements in chemistry. Here's a list of pigments that you can use more or less if you want to make magenta, cyan, and yellow primaries. Nowadays, with magenta and cyan, we know how to deal with the limitations of the traditional wheel. But as early as the 19th century, artists tried to remedy this in a different way. That's how the split primary model was created. The idea is to divide each primary color into a pair of so-called cool and warm colors. Thus, the simple primary yellow is replaced by two colors, a warm yellow pulling towards red and a cool yellow pulling towards blue. For example, cadmium yellow deep and cadmium yellow lemon, cadmium red and permanent rose, ultramarine blue and cerulean blue. The assumption is that the red, yellow, blue model is correct, but that all primary pigments are imperfect and have a bias. Proponents of this system argue that primary paints contain impurities of a secondary colors and that the result of the mix depends on the amount of impurity. This means that for each primary, it's necessary to have two pigments whose impurities tend towards the opposite secondary colors. Another more modern system is beginning to spread more and more as artists take ownership of digital tools. This is a 6-hue primary model known as the YRM-BCG wheel. Personally, I call it CMY RGB because I think it's easier to remember this way. The basis of this wheel is the RGB model, used by digital programs like Photoshop or Krita. In this model, the 3 additive primaries and the 3 subtractive primaries are distributed evenly. Intermediate colors are obtained by mixing 2 adjacent primary colors. If you are using a digital painting software like Photoshop, it's very likely that the color selector will work with this model. Starting from the main colors red, blue, and green, you can see how the remaining hues are distributed: red, yellow, green, cyan, blue, and magenta. The Monsell color system was invented by artist Albert Henry Monsell at the beginning of the 20th century. Munsell thought it was impractical to describe colors by naming them individually, so he came up with a system based on human perception that was one of the first coherent three-dimensional color spaces. It's a very consistent system, and it is still used today, both by the industry and by a relatively large number of artists. Munsell's system is founded on the three fundamental properties of color: hue, value, and chroma. The introduction of these three properties was a revolution in the world of color. It revealed the main flaw of all previous models. All had incomplete representations of color, which only took into account at best hue and chroma. Not one could unify hue, value, and chroma at the time. That's why it seemed that brown and all the shades of gray had no place in any color system prior to the introduction of the Munsell system. Because it has three dimensions, hue, value, and chroma, the Munsell color system must be represented in 3D. At the beginning of his research, Munsell tried to fit everything into a sphere, but he quickly realized that color perception is chaotic and does not fit into a regular shape. This is a second major lesson that can be learned from Munsell. Any attempt to represent colors in a regular geometric space can only lead to distortions. We must choose either a very regular geometric shape or sticking with the irregularities of our visual perceptions. One thing is certain, our vision of color is not geometric. Since the sphere did not work, Munsell's system organized the colors around some kind of tree. This tree sorts colors in three axes. The y-axis representing the value from 0, the darkest, to 10, the lightest. The x-axis representing chroma, graduated by even numbers ranging from 0, the most neutral gray, to 14, 16, or 18, depending on the chroma of the color. And finally, the colors are arranged in a circle in the plane formed by the z and x axes. Munsell divided this circle into 5 main hues: red, yellow, green, blue, and purple, subdivided into 5 intermediate shades: yellow-red, green-yellow, blue-green, blue-purple, and red-violet. That makes 10 basic hues. Each of these colors is then subcategorized into 4 substeps, which makes, for example, 2.5 YR, 5 YR, 7.5 YR, 10 YR, etc. That makes 40 hues in total. The easiest way to use the Munsell color system is to create a chart for each of these 40 hues, as if it were a book with individual pages rotating around an axis. Here is an individual chart. The name of this hue is 5RP, so it's a red-purple, exactly between red and purple. If you move to the right, colors get more chromatic. If you move down, colors become darker, and if you move up, they become lighter. If we look at another hue, you can see that the chroma and value profile is not the same for every hue. Each given hue has a specific profile. That's why this model couldn't fit into a perfect sphere. Each color has a specific code. It is given by the 3 digits of the hue, value, and chroma in this order. For example, this color would be 5RP510. It means that it has a purple-red hue, an average value, and a chroma of 10. The Natural Color System, NCS, is a proprietary color model based solely on human perception. It doesn't take color mixing into account. It's used mainly by industry. The NCS system is based on the color opponent process theory of color vision, first envisioned by Goethe and later theorized by the German physiologist Ewald Hering. We briefly talked about it in the chapter on human vision. In accordance with the opponent process theory, the NCS states that there are 6 elementary color perceptions which coincide with what are called psychological primaries: white, black, red, yellow, green, and blue. Each of these elementary perceptions is part of an opposition: white-black, red-green, and blue-yellow. Here is the color wheel obtained in the system. The 4 psychological primaries are placed equidistantly on the 4 quarters of the circle. Like Monsol's system, the NCS system has 3 dimensions. The colors are distributed according to 3 criteria: hue, whiteness or blackness, and chromaticness. It's possible to combine colors according to their degree of whiteness, darkness, or chromaticness. It's a proprietary model with a complex naming system, and it's mostly used by industry nowadays. It's almost never used by artists because it doesn't take into account pigment mixtures. It's easy to feel overwhelmed by all these different models, each with their advantages and disadvantages. Color theory can easily become a bottomless pit. It's always possible to dig deeper and find more complex systems. The real challenge is to simplify things enough to make the theory actually useful. Remember that all these systems are arbitrary. Colors are only organized because we want to organize them. The best system is therefore a system that can be used effectively. All these models are interesting to know, and they have undeniably advantages of their own. The red, yellow, blue model is very widespread, so one will easily find resources in books and on the internet. The split primary model offers more pigments and subtlety in the choice of primary colors. The CMY RGB model is easily transposable in an image editing software, and the choice of 6 primaries solves many problems. And the Monsol color system is really great for its coherence and because it is based on human perception. However, we must also have a look at all the serious drawbacks of these models. Since theory is always somehow arbitrary, there is no advantage without a disadvantage. What matters to us as artists is to know what is the most advantageous for painters, because some of these models have issues that quite frankly make them unusable for painters. The problem with the red, yellow, blue model is that it is too limited for cyan, green, and violet. So in practice, artists always need extra pigments to fill these gaps. Regarding the split primary model, it is based on theoretical explanations that are no longer relevant today. The CMY RGB model is interesting, but the connection with the real pigments is hard to do because it's based on additive mixing. And finally, the Monsol color system is certainly very detailed and coherent, but it's not really of a great help for mixing the colors and choosing the right pigments. Personally, I learned painting with the Monsol color system. It really was a revelation for me as I was a student, because it was the only model to give a real place to all the nuances of gray, brown, and low chroma colors that artists have to paint so often. But I also like the idea of integrating the additive and subtractive primaries in this color system. So I ended up using a mix of the Monsol color system and the CMY RGB model. This is what makes the most sense to me, but maybe it's only for me though. All color models must give way to actual experience. To be honest, I rarely use my color wheel in my studio. At least, I don't use it as a guide for mixing very often. To give you an analogy, it's not a roadmap, but more a traffic sign. And when you know all the roads really well, you can almost travel without ever looking at the signs? Well, it's the same thing for painting. Basically, the color wheel only provides me with a general framework, and then the mixtures are made mostly from experience. Here is a color wheel that I propose to you. Don't take it as a complete method or a system. It is simply the presentation that I found to be the most practical in my studio. I didn't invent anything. It's actually a combination of the best features of the different systems in a single image. This presentation attempts something impossible. Put the 3 dimensions of color, hue, chroma, and value on a single flat picture. To do that, I chose not to have just 1, but 3 wheels to have the 3 dimensions represented. The first wheel contains high chroma colors, the second wheel contains medium chroma colors, and the last wheel contains low chroma colors. The chroma dimension, therefore, has only 3 degrees of accuracy. It's not much, but it's always better than not showing it at all. In this picture, the key of each wheel is the value. Each hue is divided into 9 steps, ranging from very light to very dark. Thus, it is possible to visualize the value gradations that will be necessary to paint an object of a defined color. It's easy to use these wheels to create an accurate impression of volume. I chose 6 main hues, and I don't call them primaries: red, yellow, green, cyan, blue, and magenta. These 6 hues are not exactly equidistant as in the CMY RGB model. I chose to put yellow a little bit further from red, adding orange in the process to get closer to human perception, which is more sensitive to orange. This avoids green to dominate too much. Between each of the main hues are 6 secondary hues: red-yellow or orange, yellow-green, green-cyan, blue-cyan, blue-magenta, and red-magenta. Each of these 12 hues is further subdivided into 3. This brings the total number of hues presented in this system to 36, and that's enough to go around the 360 degrees of the circle. I have chosen a significant number of hues in order to have a wide variety of nuances. If we count all the gradations in these 3 wheels, 972 shades appear on a single sheet. Finally, and this is the most important thing, I didn't want this color wheel to be purely conceptual. I made sure to connect ideal colors and real pigments. So I placed the main pigments around the 3 wheels. These pigments have been chosen because they are the most frequently used. Of course, not all pigments can be represented. There are many of them, and there can also be a great disparity from one brand to another. So of course everything is just an approximation, but it gives a basic idea of where everything is. Other documents come with this picture. A mixing wheel with only hue and chroma shows how every mixture has a cost in chroma, meaning that the mixture of the 2 colors is always less chromatic than the 2 original colors. If you want to predict the result of a mixture, this is the wheel you want to use. The closer to the center, the less chromatic the mixture gets. This wheel is simpler than the 3-wheel system and may be easier to read depending on how you want to use it. In practice, here is how to use this mixing wheel. Let's imagine that you have 2 pigments. For example, quinacridone rose and cadmium yellow, and you want to predict what the result of their mix will be. So start by locating their spot around the wheel, here and there. Then draw a line to connect them. All the colors on this line can theoretically be created by this mixture. Be aware that in many cases, the line will actually be a curve that may tend outward or inward. In the case of our 2 pigments, it's a curve that tends outwards, and allows to create a pretty bright red. You can also use this wheel the other way around. For example, you want to create a specific color and you are wondering which pigments you could choose. By observing on which line the target color is, you can go up each side and discover a set of potential pigments. You just have to try them and see which ones suit you. Just keep in mind that this wheel is not designed to be a prediction instrument. It's rather a tool to give you a basic idea for your color studies. Finally, a series of charts come with this document to bring more details to all the colors of this system. Each hue comes with a color diagram built around two axes. The x-axis represents the values graduated from 0 to 100%, 0 being pure black and 100% being pure white. The y-axis represents chroma or hue purity, also graduated from 0 to 100, 0 being neutral gray and 100 being the maximum chroma that can be achieved by a color. The plus sign indicates colors whose chroma may exceed the range that can be represented in these diagrams. They are colors that are visible to the human eye, but cannot be accurately reproduced in the color space of the computer. In practice, here is how to use these diagrams. Diagrams can be used to visualize how to paint an object of a given hue by representing the shadows, halftones, and highlights. Start by defining the local color of the object, meaning its color unaffected by shadows and highlights. In other words, its natural color. Once you have found the local color, trace a bow curve that starts with black and finishes with white. Here's another example with another diagram. So the local color is here, and here's the bow curve. More concretely now, let's take the skin tones of this model. First, identify the local color. Here. Then, trace a bow curve connecting the two extreme points, white and black, and passing through the local color like this. So now you can follow this curve and premix the different shades in a closed palette, for instance, and this will help you paint by following the relationship between value, hue, and chroma. Be careful, it's indeed a curve that goes through the local color and not a straight line. You'll see that with experience you'll visualize this curve without the need to use the diagrams anymore. You just have to understand that the local color is the most chromatic color of the object and that it loses chroma as it gets closer to the shadows and as it gets closer to the lights. At least that's how our vision works. So I hope that these diagrams can help you understand that and help you improve your color mixing skills.